Stein, Lundby, R&D manager at Qualcomm, talking surface electronics.
I'd like to talk to you a little bit about what we call surface electronics. Surface electronics for us is the collection of printed, deposited electronics, flexible electronics, thin electronics. So a lot of the technologies you'll see during the next 2 days at this conference. I'd like to share some experiences we've had. Qualcomm has been involved in a form of surface electronics since about 2004. Originally we started off doing more specifically MEMS on very large sheets of glass, so systems of MEMS. And more recently we've started broadening out and actually looking at a variety of electronics. Typically what we've done is we've been working with industry players just like yourself, and we collaborate, we look at the technology, but also we've actually been doing a big focus on trying to understand the applications and try and actually identify high-value applications. Because this is, as we've heard in the last speech, one of the big challenges is identifying the high-value applications. The technology to a certain point is there, actually figuring out what it's for. And same thing with the Internet of Things. Sure, everybody talks about Internet of Things, billions of sensors. What for, right? We still have to figure out what exactly for. So you might say, well, how does Qualcomm fit in this? Is Qualcomm going to do this mobile phones? Is this all limited to cellular? And it's not. Qualcomm actually, pretty much from the early days, has been involved in a variety of technologies, providing solutions for a variety of industries. It just turns out that the most successful one has been the cellular industry, and the cellular technology pretty much took over the entire company. However, we have and we continue to, and going forwards, I expect that we have announced we will be contributing more different types of technologies in more different types of industries. And typically the model we use is we work by providing innovative solutions, so working with the industry to build up an ecosystem and grow it, and then enable others to be successful. So that's why you don't really see Qualcomm branded products, except for the occasional one here or there, and sometimes more of a demo product to spur essentially the technology and get started the industry. Then the industry and ecosystem, we actually support them to make them successful with their users. We do this based on 4 core competencies that we work on. The first one is the development of complex systems R&D. So the idea there is to be able to actually mature technology from this lab demo state to actually something that really works very well. The second one is design for manufacturability. And there are some people who say, you might have heard this, having a working system is 10% of the work. 90% is actually getting it into manufacturable form and actually being able to sell it and scale it up and make sure it works. And it's not a trivial thing, right? A lot of the products we develop, the technologies we develop, whether it be for the cell industry or the Department of Defense or others, have got essentially zero possibility for product recall. As a point of data, we sell 2 million chips a day. These chips get integrated into complex devices. These devices, like phones, get sold everywhere. We couldn't recall our products if they actually didn't work. So we have to be able to design something that's manufacturable and in a scalable way and a reliable way. The third one is supply chain management. And the fourth one is custom engineering support, which is an often overlooked element of introducing new technologies into an industry. And I think the first speaker touched about that. Very often there's this, hey, here's a widget. Here you go. And it works. And actually managed to make a difference in the industry or in the ecosystem and getting the customer to win. In particular with these early technologies requires you to get involved, because cutting edge technologies, I like to say, never really work from day one. When you launch them, there are always problems, there are always bugs, or they're not really used the right way. So before we go into this, and now our experience in surface electronics, let me take a step back and actually start give a bit more perspective. And I'm hoping to give you also a lens that will allow you to look through which you can look at the next 2 days when you attend this conference and get some perspective. So fundamentally, a large portion, predominant portion of Qualcomm's success and a lot of other similar technology companies' success has been the evolution of the mainframe to the workstation. Workstations were accessible to more people, but they were in a room like this, and you had to access the workstations. Then to bringing on the personal computers in the business environment, then the personal computers in the home environment, then the wireless connected laptops, and then finally the smartphones like this, wirelessly connected. In each one of these evolutions, right, the capabilities of the internet, of computing and the internet, were brought in to two things. One, to new contexts. Right? Originally, workstations were just research labs for government, defense, and for high-end universities and high-end companies. And then it came into actually more companies, and then it actually got into your home. So the internet now arrived in new contexts, and it actually arrived to new people. When you bring a capability like that into a new context, you immediately create the opportunity for new experiences. And that created an explosion of demand. On top of that, an exponential growth was superposed because the democratization of introducing the internet capabilities into these new environments now allowed a bunch of new people to use it, creating this network effect and a snowballing effect. The underlying technology that's actually been used, that's actually supported this, is the integrated chip, the integrated circuit technology. And it turns out the integrated circuit company, the technology, had some very nice characteristics. In particular, it's scalable and it had a very good roadmap, a logarithmic, an exponential growth roadmap that people know as the Moore's Law. And so now today in a chip like this, right, we've got what before used to be an entire room full of a mainframe, probably the size, sometimes the size of this entire room. Before you used to use kilowatts of power. Now we're talking about milliwatts and soon less. It used to cost, a computer in 1962 cost the equivalent of $25 million. Right? Today you can buy your computer that's more powerful than that one for $600 or so. Right? The cost for transistors, so the cost has dramatically gone down. The power has dramatically gone down. And of course the space has dramatically gone down. That's really the underlying technology that's been able to fulfill that and actually grow this technology. Now, where do we lie with surface electronics? So conventional electronics, if you look at the two axes, right? On one axis, the vertical axis, I've placed the setup fab costs. So they were increasingly high, but due to the scalability and the amount of people and the exponential growth, you had more and more people demanding it so you could actually tolerate this increasingly high cost. On the other side, you have the surface electronics, which deals very well with large areas, much lower setup costs. So the first mistake we've seen a lot is people trying to go from the bottom right corner and go for applications in the upper left corner. Right? Clearly, with surface electronics, you're really far away, and it's going to be very hard for you to beat this. This has got an exponential growth and a network behind it, and you're trying to go after products that actually do that with technologies that have got longer switching times, flexible. Yes, they have flexible substrates and simple fabs, but they're predominantly for performance. So the challenge we took on was to try and see, can we try and actually identify or create high-value applications that leverage crappy electronics, but actually take advantage of the better dimensions, so the dimensions that the traditional electronics do not address. And what do those types of products look like? So we had a first initial product that we tried and has had very good traction so far. And it's essentially, what it is a sensor platform. So it's composed of a screen-printed circuit on both sides. It's a hybrid electronics, meaning that we actually do use some silicon components. Why not? They're cost reduced, and as long as they're small enough. On the back side, we've got an electrode And on the back side, what we do is we print on a flexible battery. So what we do is, instead of having the traditional electronics where it's actually integrated circuits that go on a circuit board, and then you plug on a battery, and then you plug on a sensor, and you plug on something else, and it becomes fairly big and bulky and heavy and thick. Now we've got the whole thing, and the whole thing is monolithic. It's manufactured in a single plant, so that's key, because you don't want to have all the steps of assembling it all together. One side you're depositing the battery, the other side you're depositing the electronics, and then you close it up. On it, this sets a platform. We have a 3-axis gyroscope, a 3-axis accelerometer, and we're not going for high-performance electronics that's rechargeable and so on. We're going for disposable. And depending on use cases, this can last between 1 day and 1 hour and 7 days. And then the end product is a Band-Aid type of thing, what you unpeel and then you stick wherever you want for a particular application. So the first application we went for was the golf application. And the golfing application, what we realized is it's actually very valuable to measure the performance on the head of the golf, like the golf club. What we also realize is no one does it, and the reason that no one does it is that it's subject to these incredible forces. 1,500 Gs of shock load. Traditional electronics won't withstand that. It has to have a near imperceptible weight. Same, 160 miles per hour when you hit the ball and you launch it. 3,000 degrees per second. So these are really parameters that are very difficult to meet with traditional electronics. What this patch does is it measures the movements in the X, Y, and Z directions, and then the rotations in the X, Y, Z directions. And out of that, we have algorithms that convert it to club speed, ball speed, tempo, face angles, club path, and so on and so forth. So I'm not a golfer, but essentially what it allows you to do is, with those parameters, you actually can get a lot. You can actually get, with the face of the club and the direction in which it's going, you can get a good idea of the trajectory. This is a bunch of, a series of different trajectories of balls. So on the left side, you've got the face of the club in black, and the direction, so the path of the club in red. And depending on what you're trying to do, you don't actually align the two of them. And then from that, you can determine the trajectory and so on. So I actually brought my pad, I brought my golf ball, and I was going to give you a demo on stage here. And fortunately, it turns out, I learned taking the airplane that a golf club is considered a weapon by TSA. So I almost got arrested while trying to argue my way onto the airplane. but you know, so instead, I have to show you a demo. But the idea is, you'll see quite clearly, the idea is that you peel this thing off, you stick it onto your golf club, then you have your smartphone that's actually synced with it, and you get the data that's actually shown on this one. So that then show, let me see. It's supposed to do. This. That should do it. There you go. So you see the user peels on, sticks on this disposable patch. In this case, it's a driver, very thin, very light, so very little effect actually doing this. Headset. So you see the starting point, right? The golf club, it turns out when you play golf, and you start off with your golf club at the bottom against the ball, and then you take up for your swing and go down. So we don't need the GPS or anything like that. We can actually use the reference point. We use the reference point and we detect when the user is actually touching the ball as a reference point to figure out where it is and calibrate where it is in space. Because of course, this is not going to be stuck perfectly straight on the golf club. You get immediately the results. Either the results of your last shot or the results of multiple shots you've had. And then the same thing in the putter. Putter's a little bit more difficult because the putter is actually, your shot is very dependent on the surface. So if it's sloping one way or another, However, this will give you some valuable information on how you're performing. And now you're getting measurements that traditionally you would have to use extremely expensive equipment or go indoors and have these laser rangefinders and so on and so forth, cameras with just simply attached. And here's an example of some graphs pulled directly from a shot. On the left-hand side, we have the acceleration. So it starts off about 0, and then you see the acceleration. So the lowest one, the one in green is blue that goes down, is the direction of the club. The other one that's fairly big is the red one, and that's the one that's the centripetal force. And there's a peak that's actually very high, much higher. It's not depicted here, but it goes really down to a lot of power. On the right-hand side, what you see is the angles. And in particular, those angles, we have 3 little stars there, the yellow stars. Far left, and then further right, and then most right. Those 3 are reference points. So the first one is, it's figured out where the golfer is going to start while he's like this, and the hand is down. The second one is highest point, when the club is at the highest point, and the last one is the contact, the impact of the ball. So what does it look in terms of numbers? These are just preliminary. So we gave 13 tries and we looked at the numbers. This is the velocity of the club head. The first column is just accounted to say the 13 tries we had. The second column is the velocity. The reference value is the third column. That was calculated using extremely sophisticated equipment, so camera and radar based or whatever they use. And then in the last column we've got the error, and it's about within plus or minus 1%. Traditional wearable or electronics that you put on don't get on the club head, they go on your glove or elsewhere, and they've got significantly lower accuracy. The ones we tested were plus or minus 10%. So, simple thing, but very good performance and brings great value. The types of challenges we've seen were in circuit pattern printing, electrical characteristics, mechanical stress, design for mass manufacturing, meeting the cost target. So I didn't tell you, but the cost target of this thing is disposable, so you can kind of guess where I'm going for. Right? We're looking at the price where a golfer would just pick one up or pick a bunch up, play one game, so a full game, and then throw it away after. To be able to do that, of course, you have to optimize really the manufacturing process. So all of this brings me to a question, an open question for yourself, and a thing for you to ponder while you walk around the conference in the next 2 days. The integrated circuit, so known as the chip, right, was an optimized technology to bring the computing and the internet capabilities into these new contexts and to these new people. It had a huge success by doing that because of bringing it into new contexts, because of creating new experiences, and because of the democratization and the network effect. Right? When we're talking about Internet of Things, does it still make sense to use that model? Does it make sense for you to access the internet from your doorknob, from your refrigerator, from your others, so on and so forth? Or does it make more sense to actually go from the opposite direction? Start from things, high-value things like your golf club, so things that are associated with high-value experiences, like your golf club or other type of things, like your fashion clothing, and move towards the internet and essentially leverage the internet and computing to enhance that experience. So these are 2 distinct paths you can take. And if it does make more sense to start from high-value objects or high-value experiences and move and add internet connectivity to it and computing and so on capabilities, what form of electronic makes more sense? Is it the one that was designed to scale down an entire room, or is it more one of these new surface electronics forms? Thank you very much.